Welcome to another wonderful day in Calculus 3. We're going to be doing the divergence theorem today. But before we do, it's time for a meme. Why did the chicken cross the Möbius strip? To get to the same side. Ha ha! You'll remember a Möbius strip only has one side. I thought that was a good joke. And then the Klein bottle, which is the 3D analog to a Möbius strip. The Klein bottle does not have two distinct surfaces, these two distinct sides, if you will. So there's the following limerick. A mathematician named Klein thought the Möbius band was divine. Said he, if you glue the edges of two, you'll get a weird bottle like mine. Yay! And that's the Klein bottle. We saw a picture of that last time. It's in your course reader, look it up. It's a non-orientable surface. But we're not going to be dealing with Möbius strips or Klein bottles, luckily. We'll make sure that our problems are involving surfaces that have two distinct sides. So don't worry. It's fun to know about this stuff, isn't it? Okay. So let's take a look at the divergence theorem. What is it and how do you use it? When is it okay to use it? So let's do a little bit of review. Recall that the flux form of Green's it looks like this. It allows you to calculate flux equals like that. And you take the dot product of the vector field with the unit normal vector, but you don't really have to do that because you could just do mdy minus ndx. And that's different from mdx plus ndy. Remember, that was the circulation form of the Green's theorem. This one's different. And if it's a closed curve, well, then go ahead and turn it into a double integral, where the integrand is dmdx plus dndy. But from our study last week of divergence and curl, dmdx plus dndy is the divergence of f. So really, this form of Green's looks like this. You turn it into a double integral and take the divergence of f, and that gives you the overall flux through the curve. So this is a two-dimensional thing. Now, what about a three-dimensional thing? So you want flux through a three-dimensional thing. Well, we already saw flux integrals from last time. So if you want to know the flux through a surface, use a flux integral. But what about a closed surface? Because Green's is only good through a closed curve. So what about a closed surface? We're going to look at that today. So a surface S is closed if it forms a complete boundary of some solid Q. So what's an example of a closed surface? Well, a sphere. That's a closed surface. And there are some more, like rectangular boxes and things like that. Okay. Here's what you need to invoke the divergence theorem, and then we'll actually do it. The surface S must be closed. So what does that mean? It has to form the complete boundary of a solid. So some examples: spheres, I just mentioned, cubes, ellipsoids, tetrahedrons, rectangular boxes, any of those. And there's, of course, more. So if you have that, you'll be allowed to use the divergence theorem. And you also need extra criteria here. The Q, which is our solid, it must be a solid region, we'll say, solid region, on which a triple integral, triple integrals, oh yeah, we love these, which a triple integral can be evaluated. And we're going to add more criteria here, that the closed surface S is oriented by outward unit normal vectors. And the closed surface S is oriented by outward unit normal vectors. I'll show a little picture here. So here we are, 3D. Got my X, Y, and Z axes going here. And let's have some sort of closed surface here. How about like an egg? That's an ellipsoid. So let's look at the top. I put a little dotted line here in the middle. Let's call the top surface of the ellipsoid S1 and the belly S2. And the reason why I'm kind of cutting it in half like that is because the unit normal vectors that we're going to use to orient the upper half of the egg are pointed upward a little bit, up and out. So these are little unit normal vectors everywhere. And then on the underbelly, we still want the unit normal vectors pointed out. But notice how the ones on the underbelly are pointed somewhat downward. And that does matter. Okay, so S1 we have oriented up. And on the underbelly of our solid, we'll call it that S2 oriented down. Because we need everything to be oriented coming out of the surface, because we're going to be computing flux, the amount of stuff coming through the boundary. And last time we were talking about, well, it could be bananas that are going through the surface. Total flux of bananas or water or electric field or whatever. Okay, now we're ready for the divergence theorem. Here we go. Let Q be a solid region bounded by a closed surface S, oriented by a unit normal vector directed outward. There's that key thing, outward from Q. If F is a vector field whose component functions have continuous partial derivatives in Q, then when you're trying to do this flux integral, which looks like a double integral over the surface, we did these last time, and we have the dot product of F with N ds, and we talked about that. We talked about this N ds typically was negative gx, negative gy, 1 together, and then you dot product that with your vector field, equals, so it turns out you don't even have to evaluate that flux integral. You turn it into a triple integral instead, because it'll be easier. That's the motivation. And you integrate this triple integral over your closed surface, which is your solid. And your integrand is super easy. It's just going to be the divergence of your vector field. And then you have your volume element. And so from our study of divergence, you guys should be totally ready for this, because your divergence is easy peasy to get. Remember, your divergence is a scalar function that looks like dm dx plus dm dy plus dp dz. And that's it. That is your divergence theorem. So what does it mean when we're talking about the divergence of a vector field? We talked a little bit about it when we went over divergence. So there's a little bit more to it, because when you hear the word diverge, it kind of means to separate or walk away from. So it's the tendency for the field to flee from or diverge from that point. So after you do one of these, a calculated divergence, and if the magnitude of the vectors get larger as they pass through the point, then the divergence of that vector field is positive, and that point is called a source. If, on the other hand, the magnitude of the vectors gets smaller as the vector field passes through a point, the divergence of that field is negative, and that point is called a sink. And we'll look at that idea more on the next page with some little diagrams. So here, like here's a point, and notice that you've got sort of more bananas, if you will, coming out, directed out than going in. So you're going to have your divergence be positive. If on the, so that's a source. If you've got more vectors going in, that means your point is a sink. And here at this point, if you don't have more going in than going out, you got pretty much the same as flowing in as flowing out, you're going to have what they call incompressible. So let's do some examples using the divergence theorem. Okay. So I'm going to show you how easy it is to use the divergence theorem. And then on the second example, we're going to do what's called a verify, where you have to do the left-hand side of the theorem and prove it equals the right-hand side of the theorem. So, well, why aren't you doing that on example 1? Because it would take a lot longer. And we'll go over why. Okay, so let's look at example 1. Say you have a solid and it's bounded by the coordinate planes. Okay, immediately that tells me we're in the first octant. That's a cute way of telling me I'm in the first octant. Okay, and it's also bounded by the plane 2x plus 2y plus z equals 6. That's kind of like the capping surface. So I'm going to just draw this solid because I can. And you guys know how to graph the portion of a plane, right? You can find the x-intercept, that's going to be 3. The y-intercept's also going to be 3 for this plane, and the z-intercept's going to be 6. And then we got all the traces. So what does the solid look like? It's a tetrahedron, so it's got 4 sides, bounded by the coordinate planes and this capping surface. So if we submerged this tetrahedron into a bathtub of flowing water, would there be more water flowing across the whole boundary of the solid or outward, or would more fluid be going inward? Or would we end up with zero flux, where the same amount of fluid that's flowing out gets canceled by the same amount of fluid flowing in? Good to know. If we had to do a flux integral, so if we didn't have the divergence theorem on hand, how would we do this problem? So here's the slow way we would have to do it. Since Q, that's our solid, is bounded by 4 subsurfaces, basically 4 sides, Q can be written as the union of 4 surfaces. That's all 4 sides. And we would require 4 flux integrals total. To evaluate the total flux. So what are we saying? If somebody said, well, you're not allowed to use that divergence theorem in this problem, we're like, what? Yeah, you'd have to do the flux through the plane part. We could call that like S1. We do that flux integral, and we do all the stuff that we did from last lecture. Plus, and then we'd have to do another flux integral for the bottom base down here. So that we'll call that S2. And then we'd add that flux integral to, start changing colors here, this side over here, call that S3. That's sort of the YZ plane solid, or surface rather. And then finally, the last side of this 4-sided guy here, it'd be the side that's in the XZ plane. We can call that the surface 4. And if we did all 4 of these flux integrals and added up all the results, this would give us the total flux. And it would take some time, but we could definitely do it. But here's the benefit of the divergence theorem. It's a closed surface. So we're going to apply the divergence theorem instead, because we can. So what are we saying? We're saying we can get the total flux across this solid by evaluating the triple integral over the solid, and the integrand will simply be the divergence of the vector field. What's the vector field? Well, they gave it to us right there. Got components x, y squared, and z. So let's first calculate divergence of f. We know that that's going to be the sum of three partials, dm dx plus dn dy plus dp dz. Great. And what is dm dx? Knowing that m, n, and p are the components, so the derivative of x with respect to x is 1. The derivative of y squared with respect to y is 2y, plus the derivative of the last component z with respect to z is 1. And so this is just going to be 2 plus 2y. Okay, cool. So our total flux is going to be equal to triple integral, and we're going to have 2 plus 2y here. And then this dv, the volume element, I'm going to just use my personal favorite order of integration here, dz, dy, dx, because that's nicer. And so what are those limits going to be for all three of these integrals? You got to be very careful when you do this part. You have to use all the knowledge that you used and got from the last module of setting up limits on triple integrals. And that's what's so cool about this final chapter, because it is the culmination of everything that you've learned before. So you got to be good at triple integrals. Yeah. Yeah, fun. Well, I didn't want to do that. Try again. Pen to document. Okay, so what do we know? We've got this plane portion here that's the capping surface, and we see that the base of the solid in the xy plane will help us figure out what's going on in the xy plane. So what is going on in the xy plane? Remember, the plane equation is 2x plus 2y plus z equals 0. Set z equal to 0 to see the trace of the plane in the xy plane. So we get 2x plus 2y equals 6. Solve this for y. I get y equals 6 minus 2x over 2. If we reduce, that's 3 minus x. So it turns out that the trace is that guy right there. And we're in the first octant, which means we're in the first quadrant here in the xy plane. Okay, so cool. So here I hope you can see that the limits for x, if we have that be the outermost integral, will be 0 to 3. And if we put our little man in there, the little man's head is touching the line. So that's the upper limit for y. And then his feet are on the x-axis, which has the equation y equals 0. So the 0 and 3 minus x will be the limits for y. And then what about z? Well, z is going from the xy plane, which is z equals 0, up to what? If you solve this plane equation for z, you'll get z equals 6 minus 2x minus 2y. So that will be the upper limit for z. That's the innermost integral. And then for the middle integral, we got the limits for y, 0 and 3 minus x. And then we have 0 and 3 for the outermost integral. And let's go ahead and do this. Okay. Now, when you're doing one of these integrals, I want to see all your steps. So please don't skip steps. I'm seeing some folks skipping steps here and there, not showing me the intermediate step of, say, the antiderivative. I need to see that, all of it, if you want maximum points. So let's integrate with respect to z first. That means this 2 plus 2y just looks like a constant multiple. So I'm just going to copy it down and multiply that with z, where z goes from 0 to 6 minus 2x minus 2y, like so. And then we'll plug in that upper limit and then minus the lower limit. Okay, so that's going to be somewhat of a hot mess here. Yeah, sometimes these triple integrals get a little tricky. Now what? Well, you're going to have to distribute. you know, some algebra here. So you're going to distribute this 2 and get 3 terms. So 2 times 6 is 12. 2 times negative 2x is minus 4x. 2 times negative 2y is minus 4y. And then you're going to distribute the other term. Oh, boy. We'll have plus 2y times 6 is 12y. 2y times negative 2x is minus 4xy. 2y times negative 2y is negative 4y squared. So this is a big mess. Are there any terms we could combine maybe to make it look a little less terrible? Well, I guess we could combine these y terms here. And that's pretty much it. I think everything else is like, oh boy, oh well. So we're going to have 12 minus 4x plus 8y minus 4xy minus 4y squared dy dx. Okay, keep going. Yeah, you can't use your calculator yet. That's not fair. If I do say in the directions, okay, you're good to go, use your graphing calculator to complete the integral, that means for the last and outermost integral only. So we still have to integrate the middle integral, which now is the innermost, with respect to y. So what is that going to look like? Okay, that'll look like 12y minus 4xy plus 4y squared minus 2xy squared minus 4/3 y cubed. This thing will be evaluated between the limits. Oh boy, this is going to get kind of messy. I know. Plug in that 3 minus x and look at all those y's there. Ooh, boy, that's going to look terrible. I know. I'm just plugging in everywhere I see a y. I'm putting in 3 minus x. Oh boy, this is nuts. Okay, well, this is where you call your friend who's in a Calculus 1 class and you go, hey, buddy, I heard that you've been working on integration now. You're finally getting to learn how to do integrals. Why don't you go ahead? I'll pay you 50 cents. Go ahead and do this for me. Right? Okay, I don't have any friends either, but if I did, I would I would ask them to help me out. Okay, so let's just go to our graphing calculator and let the graphing calculator do the rest of this for us. Because look, we're tired. We don't want to do something that's a Calc 1 problem. So first of all, make sure you're in the right mode. Oh, I'm in parametric mode. That is not going to work. Make sure you're in func mode here because we're going to be integrating a function of x here. So this is where you go hit the math button and then see at the bottom where it says FNINT, the number 9 choice. I'm just going to hit number 9 and then enter in all the pertinent things. So it looks like they want the lower limit. Okay. Oops, I hit enter. That wasn't good. And then, oh, they want to know which variable I'm integrating with respect to. That would be x. Okay. Let's do the upper limit. That's 3. And then we got to do, oh man, they want me to type all this in. Are they nuts? Okay, well, let's do it. 12 parentheses 3 minus x. Again, this is where you need to get somebody to do this for you. Minus 4x parentheses 3 minus x. If I make a mistake, make sure you say something. Plus 4 parentheses 3 minus x squared. Okay, minus 2x parentheses 3 minus x squared minus 4 parentheses 3 minus x cubed divided by 3. And I think that's it. I'm going to hit enter, see what happens. Woo, fingers crossed. 31.5. Okay, and let's look at our frac and use the frac command, number 1, and hit it. Yay! And that is the right answer, 63 halves. Thank goodness. And that concludes that example. Woohoo! Okay, so I'm going to say graphing calculator involved here. And then we got 63 halves. Okay, now what does that mean? That means since there's more flux or bananas coming out of this solid than going back in, we say that we have a source. And Dr. Vallone, may he rest in peace and may his memory be a blessing, one of my graduate advisors, he had a funny little visual for this. He said, yeah, you know, when you've got this solid and there's more stuff coming out than going in, think of a leprechaun sitting inside the solid, spitting out more fluid, so that more fluid's going out than going in. And on the other hand, if the leprechaun is sitting inside your solid and drinking in all the water or whatever is coming in, that's when you have a sink, because he's sinking all the water or whatever. Yeah, so if that helps you visualize a source and a sink, so be it. Okay, so we computed the total flux through this tetrahedron, and it was a positive value. So more water is flowing out of this solid than flowing back in. It's a source. Next up, example 2. Let's say you're given a solid region that's bounded by the paraboloid z equals 4 minus x squared minus y squared and the xy plane. Okay, so that paraboloid is kind of cute. It's a downward facing paraboloid with the vertex there at 4, 0, 0 on the z-axis. It's bounded below by the xy plane. Okay, now this bottom plate here, if you wanted to find the trace of the paraboloid as it cuts through the xy plane, just simply set z equal to 0 in your plane or in your paraboloid equation, and you would get 0 equals 4 minus x squared minus y squared. And then when you rearrange this equation, aha, the trace is a circle centered at the origin of radius 2. Okay, that's cool. This is the base of your solid. So we're going to do a verify. So verify, remember, is you have to do the left-hand side and get some answer. And then you have to do the right-hand side and get an answer. And then hopefully they match. Oh, no. Okay, so we're going to do this left-hand side first. And this is going to be a little bit of a pain. The question is, how many of these flux integrals do I need to do? So how many sides does this solid look like it has? Or how many surfaces total is it made up of? Anybody have a clue to that?
Would it be 2?
Yes. Good. So there's 2 surfaces that we have to worry about. So we're going to do the LHS, the left-hand side first. Okay, that's this. There's 2 surfaces total. You've got the bottom. How about if we call the bottom S1? So we're going to have to do a flux integral for S1. So what do you mean? It's got, well, we're going to go double S1, the vector field dot NDS. That's going to be the flux that goes through the base of our solid. Now, then we're going to have to do a second flux integral, because the paraboloid portion itself, that's a surface. We'll call that S2. So that's sort of the other surface here, the rest of it, S2. And so we're going to have to do another one of these flux integrals, and then we'll add the results together and we'll get our final answer. So that's the strategy here. Easier said than done. And then we'll do the right-hand side. Okay. Are you ready? So let's do the bottom first. Okay. So the S1. Now S1, that base plate, we want to find an obvious outwardly directed unit vector, okay? So we want this N here to be directed outward. Now notice that to be directed outward from this solid, this normal vector from the base plate here is pointing vertically down. And that base plate, if you had an equation for it, would be z, which is equal to little g of xy, which is equal to 0. That would be the equation for that surface. That's right, z equals 0 is a legitimate surface equation because it's basically the entire xy plane. And so what would, when we did these flux integrals last time, remember the NDS portion was negative gx, negative gy, 1 if you were oriented upward. But we don't want that one because we need it oriented downward in order to be out. So we want the opposite in sign, gx, gy, negative 1, so that it's oriented outward, when in this case, downward. So what is gx and gy if the gxy is 0? Come on, quick, tell me.
Is it 0, 0, 1?
Yeah, 0, 0, negative 1, because we want it oriented down. We want this vector pointing down because we need it oriented outward. Okay, so now we're ready to do the flux through the bottom. The flux through the bottom, I'm going to go in slow motion here, but write down fast. You've got F dot product with NDS. So you've got, when you turn this into a regular integral, yes, you're going to do the dot product, and you're going to take this 0, 0, negative 1 because we needed it oriented down in order to be oriented out. Now our vector field here is 2zx and y squared, but we have a little bit of a problem here. Does anybody see it?
We have a z.
Very good. You're not allowed to have a z in a double integral. Yeah, excellent. So we need to replace the z in this double integral, since it's only allowed x's and y's, with what? Anybody have a clue? I'll give you a hint.
The equation on the top.
4x minus 4x squared. Yeah, 4 minus.
Well, you would think it would be that, but I claim it isn't for this problem.
Is it the 0 that we found?
Yeah, remember that we're doing the base plate. So we're not doing the paraboloid this moment. We're doing that surface S1. So you're going to replace it with z equals 0, because that's what we're doing in the xy plane for this flux integral. Don't worry, we'll get a chance to replace with the paraboloid. So that's really just going to be a big fat 0. And now when we take the dot product, we're going to have 0 times 0, which is 0, and then x times 0, and that's a big fat 0, okay. And then y squared times negative 1, okay, dA. So what are we going to have? We're going to have negative y squared dA over the region, and the region is the circle. And I'm going to save this for later. If we were going to finish this out, I hope you realize we would have to convert to polar, because the base of the solid is a nice circle, and you just convert everything to polar here and do it. But how about, if you don't mind, I'm going to pretend I did the whole thing, but you'll see in a moment why I'm going to stop. Okay, so just save that for later. And now let's do the other surface, the paraboloid portion, and we'll do this flux integral next. Oh boy. And then we're going to add the results. Remember, that was our strategy to do the left-hand side. Wow, this is taking us forever. Yeah, I know. Okay, so for S2, that's the paraboloid portion. The normal vector is going to be negative gx, negative gy, positive 1, so that it is oriented upward. Because if you look here at the diagram, ooh, no, not so fast. We want these normal vectors to be oriented upward. So that's why we pick the negative gx, the negative gy, and the positive 1. And remember, our g is the paraboloid. Okay, so when we take the partial of that with respect to x, I get negative 2x. But remember, we're going to take the opposite of that. And this is where students screw up. is they forget the opposite and then they lose a whole half a letter grade on the final. And that's a real bummer. And then here we're going to take negative gy, so negative 2y. And then we have a positive 1. So this normal vector oriented upward is going to be 2x, 2y1. So now what? So now the flux through the paraboloid portion of our solid, we're calling it S2. We'll turn it into a double integral. We're going to take the vector field and dot product with 2x, 2y, and 1, and then we'll figure out what we'll do for the volume element. So remember that your force field is 2z x y squared, but now you're going to replace this with the paraboloid, because we are working on the paraboloid part of the surface. So what is that going to be? Yeah. Haven't even done the dot product yet. I know. Wow, this problem is taking a long time. I know. I'm sorry. So we replace with the paraboloid. Okay. Let's see. So, well, before I take the dot product, let me distribute the 2. And you don't have to, but I'm just going to follow my notes here. What do I have? 8 minus 2x squared minus 2y squared. And then we have an x and a y squared. And then we're going to take a dot product. Oh, yeah, it's going to get really kind of gross. All right, so here we go. Let's do the dot product, shall we? You're going to go, what is that times that? I'm just going to write it down. We got 8 minus 2x squared minus 2y squared times 2x plus, and then let's multiply the y components together. Finally, do the z components together. Oh, great. And then this whole mess, yeah, this is a pain in the Butowski. Okay, now, I'm not stalling, okay? I would want to convert to polar, okay? You got it, you know, r d theta and all that, but not yet, not yet. The reason why is, remember, this is for the paraboloid port. Oh boy, I didn't want to get the calculator out. Let me get rid of that. That's just driving me nuts. Okay. So what I want you to see is this is this flux integral here. Let me just copy it all down. I know it's like, really? Yeah. That's just pretty gross. Let's see, that's 2xy. And then this is y squared. And then dA. And remember, we're going to add that to the other flux integral, which I said, hey, save that for later. Well, I'm going to bring him into the conversation now. Hey, guy, come and help us out, will ya? Okay. Yeah. Now, these r's here, I claim, are the same r. Both of these flux integrals are going to be evaluated on the base of the solid, the circle centered at the origin of radius 2. So what's nice about that is that we can combine both of these flux integrals into one. And why is that so cool? Well, it's cool, not really super cool, but this y squared adds up to the minus y squared and they cancel. Okay, cool. But then what? Well, bad news, we're still going to have to deal with this stuff. So yeah, you would convert to polar. So how would that work? Well, you'd have 8 minus 2 and then x squared plus y squared. So I'd have like 8 minus 2r squared, and then this 2x would be 2r cos theta, and then plus 2xy. That would be 2 times r cos theta, r sine theta. I know. And then you'd have r drd theta, and then you'd have theta going from 0 to 2 pi and r going from 0 to 2. And if you don't mind, I'm like really tired, and I'm just going to say, etc., etc. I'll let you do the rest because it's just like, and the answer is 0. I'm not making this up. So the total amount of bananas flowing in and out of this solid, if you put it into a jacuzzi filled with flying bananas, would be 0. The same amount of bananas flowing into the solid is the same amount as flowing out. So it's incompressible. And if it were water, and you dropped it into your jacuzzi, then the amount of water flowing in is canceled by the amount of water flowing out. So your overall flux is 0 for the whole solid. Pretty interesting, huh? Aren't you excited? You're like, all that work just to get a 0? Man, that's nuts. Yeah, that's crazy. Can I explain why there's 2 surfaces, Kobe? Sure. So, whoa, I don't know what just happened. So look at this solid. If you can imagine, if you had to construct this solid out of, butcher paper or something, I don't know, so just think of some sort of material you could use to create it. The paraboloid is one whole surface itself. It's the capping surface. So that counts as one surface. And then the bottom plate, the base plate, is your second surface. Does that help? Why you have 2 surfaces? I hope. Sort of, kind of. Okay. Now, folks, we're doing a verify, and we're only halfway done with a verify. Really, all that work, and we're only halfway done. I claim we're really more than halfway done. We did do the left-hand side, the LHS, left-hand side. We're done. The answer is 0. Okay. We need to do the RHS, the right-hand side. We still haven't done that yet, because that means we're going to, see the divergence theorem in action. You should be super excited. I am. I'm really excited. I'm excited for you, because this is like some of the super fun of vector calculus. It's coming into action now. So RHS, right-hand side. What does that mean? The total flux through this interesting solid can be calculated by the triple integral. Q means the overall solid. And we've got the divergence of F as the integrand. Fine. Now remember the vector field they gave us. I'm just going to copy it down here because I forgot what it was. I'm just looking at my notes. Okay. So what is the divergence of F? We know that's going to be dm dx plus dm dy plus dp dz. And there's m, and there's n, and there's p. Okay, cool. Let's do it. Partial of m with respect to x. Well, the partial of 2z with respect to x is 0. Okay, great. Partial of n with respect to y. Well, when I differentiate x with respect to y, I get a big old 0. And then finally, dp dz, if you take the partial of y squared with respect to z, I don't know about you, but I get 0. Oh, big old 0. So what does that mean? That means my total flux is calculated by taking a triple integral of 0 over my solid, which gives me a big old 0, and that is the final answer. And so now let's take a quick survey. Which side did you prefer? Did you like doing the left-hand side of this equation, which led to all of this work? Or did you like doing the right-hand side where, voila, we were easily able to get the answer? What do you guys think? Who's with me? Aren't you loving the divergence theorem right now? Yeah, the right side, yeah. So here's what you should say. I heart the divergence theorem. Because you should. It's awesome. Saves you a lot of work. Good God, that was nuts. So since we got 0, it's neither a source or a sink. There's no leprechauns involved. Yeah. Now remember, you can only use the divergence theorem for closed surfaces. Like if you have a surface and it isn't closed, then you're back to doing a regular flux integral, getting the n ds with the negative gx and the negative gy and all that other good stuff. And yeah, our leprechaun took a break for this problem. Thanks, Angel. You're right. So I hope I have convinced you how awesome the divergence theorem is. Yeah. So, okay, let's take a look at a meme and then I'll give you a problem to work on. My friends, I almost never evaluate surface integrals, but when I do, I use the divergence theorem. The most interesting man. Yeah. Okay, so here we go. I'm pulling this out of a completely different book, okay? So you and a buddy are going to try doing this problem. You think you can do it? Sure. I just showed you how to do it. So it's not too hard. So how about find total flux through a solid bounded by the plane 2x plus 4y plus 2z equals 12 and the coordinate planes. Okay, so you know it's going to be in the first octant, right? I'm giving you a hint. And the vector field is this vector field right here, fxyz is equal to 2x minus y I hat minus, be careful with that minus, the quantity 2y minus z j hat plus z times k hat. Okay, so there is your vector field. Everybody got that?
Just give me a moment.
Okay, copy it down. Nice, nice. And then while I'm doing that, I'm gonna go ahead and queue up some breakout rooms for the folks that are really here, the few, the proud. Well, let's see, why is that? There we go. Okay, once I get you into the breakout rooms, turn on your mic, talk to your buddy, and see what you can decide this total flux is going to be. Good luck. Let's take a look here. So you want to find the total flux through a solid. It looks like it's going to be a tetrahedron bounded by this plane. And, you know, you're going to have you're in the first octant and you got a vector field here. So let's go ahead, since we know the total flux is going to be done via the divergence theorem. Let's go ahead and get the divergence of F. How hard could this be, right? So we know how to get divergence. It's dm dx plus dn dy plus dp dz. And I've got my m, n, and p here, those components. What do I got? 2. And don't forget this minus here. You might even want to distribute it just in case. So the derivative of n with respect to y looks like it's a minus 2. Ooh. Plus, okay, dp dz, that looks like it's just a 1. Oh my goodness, our divergence is just a 1. Did everybody get that? I hope so. So the total flux is going to be a triple integral over this tetrahedron with the divergence being the integrand, but that's just a 1. So what does that mean? That means that we have a regular triple integral with a 1 as the integrand. And when we have that, that's just the volume of the solid. So hopefully you remember from when we started the multiple integration module and when we started to look at triple integrals, a triple integral where you had a 1 in the integrand, that represents the volume of a solid. So it's just the volume of this tetrahedron. Yeah, really? Yeah, and if you were to draw the tetrahedron, you know how to draw a portion of a plane. You'd have what? X-intercept of 6, Y-intercept of 3, Z-intercept of 6. So this is the capping surface right here. And yeah, you probably want to solve it for Z so that you get your bearings there on what the limits for Z is going to be and what the limits for X and Y. So Z looks like, after I start subtracting some of these terms and then dividing by 2 and reducing, it looks like 6 minus x minus 2y. Okay. So then in the xy plane, if we're going to look at the trace, set z equal to 0 here. And when you do that in the plane equation, you get this. And then if you solve for y, you can see that line. So you'll go, okay, 4y equals 12 minus 2x. So y is equal to 1/4, 12 minus 2x. And that looks like it's going to be 3 minus a half x. Oh boy. So then what? Well, you know, yeah, what do you mean? Yeah, so you're going to have like that, right? So you're going to have, this is your region R in the xy plane. That's y equals 3 minus 1/2 x. So now what you can figure out is your flux is going to be triple, triple, triple. I'm going to choose dz, dy, dx as my favorite order of integration. And so what do I know about x? It looks like the outer limits there will be 0 to 6. The middle will be 0 to 3 minus 1/2 x. And z goes from the xy plane, which is z equals 0 to, what was our z equation? That guy right there, 6 minus x minus 2y. So there we have it. If you get this far, of course, I'll give you partial credit because, hey, setting up the triple integral is basically representing half the battle, right? It's like, that was the hard part. Makes me tired. Now we get to integrate. This isn't too hard to integrate. It is going to get messy again. When you integrate 1 with respect to z, you're just going to get z, and then you have your limits for z there. Okay. And then you're going to go, okay, so what am I going to integrate now? Now you have a double integral left. And you're like, okay, I got to do that with respect to y. Okay. So that looks like I'm going to have 6y minus xy minus y squared. And the limits are not pretty. You know. So you know what I want to do now? Yeah, I think I'm gonna, because I mean, I could start distributing here. You know, I'm gonna have 18 minus 3x plus a half x squared minus. I definitely don't want to FOIL that out. I could probably just use u sub on this right here. And then these guys I could probably integrate term by term by term and make it happen. So I could do it, or I could call one of my friends in my Calc 1, one of the Calc 1 classes and go, hey, for $1.50, I'll pay you to do this one for me. But I mean, this one isn't that hard to do by hand. It's a little bit of a pain. But if we go ahead and type this all up into the calculator again, by going to math and then the FNINT, and what do we have here? 0 to 6, and then we're going to have this. I didn't write this all down. Somebody help me out. 18 minus 6x plus a half x squared. Okay, 18 minus 6x plus, I'll just do 0.5 x squared, and then minus, and then it looks like we had that 3 minus a half x. What was that again? Was it squared? Yeah. Okay. 3 minus a half x squared. And then we have to tell the calculator, yeah, we want to integrate with respect to x. Okay, go for it. Let's hit it. 18, woohoo! And I believe that is the right answer. Okay, so we're good. So it looks like it's a source. So there's more water coming out across the surfaces than going back in. Okay, how's that for you? Not too bad, right? Okay, let's do one more example and we'll call it a day. I want to show you that all that study that you did and your module of triple integrals is not for naught, okay? And here's a meme, studied everything except vector fields. 80% of the test was vector fields, Green's theorem, Stokes' theorem, and the divergence theorem, which all involve vector fields, of course. So take a look at example 3 here. You've got this solid region, okay? And what does the solid look like? Well, it's bounded by a cylindrical surface. Remember, cylindrical surfaces are missing a variable, and you first graph the generating curve, which happens to be a circle centered at the origin of radius 2, and then you whoosh it in the direction of the missing variable. So you're going to get a cylinder, and they're telling you the boundaries of the cylinder. It's bounded below by z equals 0. Well, that's the xy plane. So there's the base plate in the xy plane, and by z equals 3. So it goes as this cylinder. It looks like a can of height 3. Fine. So they want the total flux through this cylinder. Fine. And we're going to use the divergence theorem to evaluate this flux integral, because we know that this flux integral, when you're using a nice closed boundary, you can convert to a triple integral, because the divergence theorem says it's okay. And they're giving you a hint. Uh-oh, cylindrical coordinates. Oh man, you guys remember that? Cylindrical coordinates. It's not going away. It's going to come and help us out here. So let's go ahead and get the divergence of F, because we've got M, N, and P. And so we know that the divergence of F is dm dx plus dn dy plus dp dz, 3x squared plus 3y squared plus 3z squared. Now, why are we converting to cylindrical and not spherical? Because some people might look at, hey, 3x squared plus 3y squared plus 3z squared. That kind of looks like maybe spherical, because the solid is not a sphere or a portion of a sphere. So it would be really hard for you to convert this to spherical. I wouldn't. I don't like pain. Because we have a cylindrical surface, cylindrical coordinates are the best bet. So this is going to go there, but what I'm going to do is I'm going to factor out a 3 from the first 2 terms. And remember, when you convert to cylindrical, z just stays himself. Z is just z. So it's like, oh, that's not too bad. So then you're going to go, okay, I got a triple integral. I have 3r squared plus 3z squared. And then remember that your volume element, dv, for cylindrical is r dz dr d theta. Be a pirate. And the base of the solid, which is just a circle centered at the origin of radius 2, tells us it's pretty easy to start putting limits. Theta is 0 to 2 pi, r goes from 0 to 2. And they told us the limits of z. They said z is 0 up to 3. You know, the top is just a horizontal plane, z equals 3. So z is constants. And so now what? I would first distribute this r so I don't forget about it, because, you know, I'm apt to make a silly mistake like that, and that would be bad. And then I will go ahead and integrate with respect to z. Okay, so the first term, 3r cubed z plus, and then this term would be what? rz cubed. And I'll have z going between the limits of 0 and 3. So the 0 is going to make everybody 0. So I just have to worry about the 3. So the 3r cubed times 3 plus r times 3 cubed. What do I have here? 9r cubed plus 27r. Yeah. Okay, so 9r cubed plus 27r is our new integrand, and we're going to integrate that with respect to r. Okay, not too bad. 9/4 r to the 4th plus 27 halves r squared, and r goes between 0 and 2. Not too bad. And the good news is now we're just going to get a constant. So what the heck is this? 9/4 times 16 plus 27 halves times 4. I think this adds up to 90. Just a multiple. So my last and final integral is just integrate 1 with respect to theta. That's just theta going from 0 to 2 pi. Final answer, 180 pi. And this is a positive number, so that means we have a source. So the leprechaun is sitting inside the cylinder going, blowing out water. More water going out, then coming back in. And so this is really a nice example. I pulled it from my own personal calculus book when I went to high school. I know, I still have it. It's right here, folks. Have I showed this to you before? This book is really old. It's older than all of you. Okay, maybe even put together. Haha. And this example is a nice example where you get a triple integral and cylindrical coordinates come to save the day. And that concludes today's lecture. And we'll finish up some more fun and play with divergence theorem next time. Okay, everybody.